All right, everyone. So yeah, I'm Aryeh Brill. I'm a PhD student at Columbia University. And so I work in the high energy astrophysics using ground-based instruments. So this is the very high energy range of tens of GeV to hundreds of TeV gamma rays. And so these gamma rays are, so how we detect them is these are actually absorbed by the Earth's atmosphere. But as they will decay into a jet of highly energetic particles. And these particles are moving faster than the speed of light in air. And so they'll emit a cone of Cherenkov radiation. And this Cherenkov radiation hits the ground and produces a light pool of blue light, which we can detect with an array of special optical telescopes. Telescopes with nanosecond time resolution and a pixelated camera. So they actually take images of these showers. And so with this technique, we can study a wide variety of high energy astrophysics. We can look for things in our galaxy, like pulsars and supernova remnants, extragalactic physics, mostly blazars. And we can also place limits on the decay of dark matter into gamma rays and other particles. And we can even study cosmology by looking at the absorption of gamma rays over cosmological distances. And so I'm part of the Cherenkov Telescope Array, or CTA. And this is the next generation Imaging Atmospheric Cherenkov Telescope Array, IACT. And it consists of two sites. There's going to be one in the north at La Palma and one in the south in the Atacama Desert in Chile. And each site will have dozens of telescopes of different sizes, small, medium, and large-sized telescopes. So look at the high, middle, and low energy regimes of our energy range. And I'm also part of a current generation Cherenkov telescope, Veritas, which is located in Arizona. And that has 4 telescopes of about the, you could say, the medium size. And so the way that we detect these gamma rays, so when the light falls in the light cone, each telescope that's in the light cone will take an image of the shower. And these images are modeled as an ellipse. They're fit to an ellipse, and this ellipse is parameterized. And then the next step is that all these parameters from the individual events are combined using a weighted sum or a weighted combination that takes into account the geometric relationship. And we use those array level parameters to reconstruct the event, the arrival direction, the energy. And these parameters can also be used as features for a machine learning algorithm like a boosted decision tree. And this technique is very powerful, but there's a catch that for every gamma ray that we get, there's also 1,000 cosmic rays that produce very similar air showers. And this gives a big background which we need to reject. And that's done by using the shower shape. So here are shown 2 simulated air showers from a gamma ray photon and a cosmic ray proton. And you can see the cosmic ray has a much wider distribution, it's a messier shape due to the complicated hadronic interactions within it. And so we see that as a wider width of our image. And so this can be used as a parameter to cut on to reduce the background. But we want to go further than this. All of the work that's been done is with these parameters, but there's a lot of information in the original images, all of these pixels that we're currently throwing away. And so we want to go forward and further improve the sensitivity of our arrays. We want to have a machine learning algorithm that is able to access an image and do some computations and then produce a classification. Unfortunately, nowadays there is such an algorithm, deep learning with convolutional nets. And so we already heard a lot about this, so I won't go into detail. But just to recap, this is a machine learning algorithm, consists of a set of layers. Each layer has a set of filters, where each filter computes the same function, but tiled along at each position on the input. And applying deep learning to Cherenkov telescopes comes with a number of special challenges. So I'll just go over what some of those are. One is our data doesn't consist actually of images, but rather a set of images, because each telescope that triggered produced an image. And furthermore, all of these images are not all the same, because they come from different sizes of telescopes. The cameras are different, so the images are different. Each size of telescope might have multiple actual models, different telescope types, so that's an additional problem, and those aren't the same. And then also there's a fact that only the telescopes that fell within the light cone actually triggered and produced data. Telescopes over here, they don't have any data. And so we need to account for that as well. Another problem And I should say that there's some approaches that solve some but not all of these problems, and I'll show some results at the end using those methods. Another problem is how to apply convolutions to hexagonally spaced pixels, because these cameras, the pixels are often arranged in a hexagonal grid. And of course, all the deep learning methods, these are matrix operations. They assume square inputs. And so there's two main approaches you can think of to solve this. One is modify the data, so do some interpolation or resampling to convert the images. Another one is to change the convolution algorithm itself to do one that naturally takes in hexagonal neighbor relationships. And that's not something that I've been working on, but it's an active research area in this field. And then finally, in order to train these models, we need lots and lots of labeled training data. But for these problems, unlike some other fields, we don't have expert labeled data. It's just not something that people do or really are able to do for these sorts of images. So we get our data from simulations. And one issue that right now we're not at the stage where it's a problem, but in the future is because we're training on simulations, we're going to have to account for the fact that simulations may have some subtle systematic differences from data, which more advanced algorithms, these deep learning, could start to pick up on. All right, and so the way that we've been working on this, so my group at Columbia and others, we've developed two Python packages to solve this problem. Image extractor, which takes the simulated data and produces it into a format that's suitable for machine learning, HDFI file format, and CTLearn, which then takes that data and then applies a deep learning model using TensorFlow. And both of these packages are open source and available on GitHub. So CTLearn is a high-level Python package for using deep learning for IACT event reconstruction. And one key thing about it is that this is meant for any sort of Cherenkov telescope. It's not specific to just, for example, CTA or Veritas, but is modular and can be used by any member of the community. And I'll just go and I'll say some of the main features about it, and then before ending with some demonstration of the results. So one important feature is that it's configurable. So all settings are defined in a single configuration file. And the idea here is to encourage reproducible training and prediction to avoid the situation, certainly this has happened to me, where you train a great model and then months later you want to write it up and can't remember exactly what every specific setting was. Here it's self-documenting. Every setting is stored in the file. And CTLearn is also not specific. It's not mandated here's our exact model, but rather you can import any TensorFlow model that you choose that obeys a generic signature. But we also include some of the models that we've been using as well, developing ourselves. It can be run either from the command line, or you can import it as a module into your Python script. And then supporting this, there's a backend of 3 different classes to prepare the data for applying to your model. There's data loader, which will load the data defined in our data format and then yield NumPy arrays. Data processor, which applies pre-processing and in the future augmentation of the data, especially in ways that are specific to what you want to do for the Cherenkov telescope images. And image mapper, which takes the images and transforms them into a square array, which especially for the hexagonal cameras is non-trivial. And so this is implemented for all CTA telescopes as well as Veritas, and we want to extend this to all of the telescope types in the community. And I should say that the data loader and data processor are completely general, so the only thing that needs to be modified to add more telescopes is just this image mapper. All right, and so to wrap up, I want to show just demonstrate that it works. And so this is using CTLearn to train 2 kinds of models. Single telescope models, which I'll explain, and then an array level model. These are all non-optimized or anything. They're trained on a small sample data set. The point here is to demonstrate that CTLearn is the first package that's able to train on data from multiple different types of telescopes. And all of the configuration files are available online. All right, and so here it is. So this is the simplest case. So this is ignoring the fact that these telescopes are in an array, but just looking at one telescope at a time, classifying that image with a simple convolutional net of several convolutional layers. And the takeaway here is that it works for all of these, all 7 CTA telescope types with reasonable results. But don't read too much into these specific results because this is not optimized and it's on only a small training set. And then, so one approach that this is seen in the literature, this has been done by the Hess collaboration and others, is combining a convolutional network with a recurrent network to handle multiple telescope input. So the first step is that each image is fed through a convolutional net to produce a vector representation of the image. Then each of those is fed into a recurrent network that stores a memory of what has been seen previously. And then the outputs of all of those recurrent steps are concatenated, fed into a fully connected layer, and then fed finally into a classifier to do the classification on the image. And so here, the advantage is now we can take a variable number of inputs. Because in any given event, there could be 1 telescope that triggered, there could be 4, or another number. The disadvantage is it's not yet able to take in telescopes of different types. It's still required that each telescope is of the same type. And here's the results from that, again with all of the telescopes. And the takeaway here is that the performance is improved from the single telescope, which is very good. And here I can't show a comparison to existing methods, some of which are still under development actually for CTA, but in other results this has been shown to exceed the performance of the typical boosted decision tree methods. All right, and so to conclude, IACTs, especially the upcoming CTA, are an essential tool for studying the universe at high energies, and I would add, especially in conjunction with other multi-messenger astrophysics. But key to this is the key to the sensitivity is reconstructing these events, both in reconstructing the events and also rejecting the background. And neural networks are a key way for the next step to improve the sensitivity. And this is an area with great promise, but also a number of challenges. But we've started to tackle these challenges. CTLearn is a general modular framework for applying deep learning on ICT data, and it's open source. It's under development on GitHub. Thank you.